Welcome learners. Today we are continuing the module 2 of week 1. In our last lecture, what we have discussed about the approach 1, that is, what is that? Check and guess method. And in that method, what actually we are doing, if x into x is greater than n, then decrease x by an amount d. So x, this is the equation, right? And secondly, if x into x is less than n, then we increase the x by amount d, right? These are the two updation rule we have used in approach 1. And then we also said we need to update d as well. How should we update d? If x changes the direction of the movement, then update d using this formula, that is di equals to 1 by 10 of di minus 1. So these are the basically three things we have discussed for approach 1. Now let's learn a new approach which is not that much different from approach 1, but only the updation rule is different here. Now let us discuss the approach 2. Now we are taking the same example, n equals to 20, and we need to find out the root of 20, right? So approach 2 is similar method. It is also a check and guess method, but only the updation rule is quite different here. So since it's a check and guess method, you need to do the first step. You need as choose x arbitrarily. So in this case, we are choosing the same value, x0 equals to 5. So this is what that point, I have marked it. Now, the next step, what you will do, you will check whether this value square is equals to n or not. So we have done this. If it is n, then we will stop. But we found that it is 25, which is not equals to n. So that means we have not found the actual root. So we need to proceed further. So therefore, the step 3 is to update the x for the betterment, right? So we should get a more accurate value x, which is more close to the actual root. So now here in this case, we will use the updation rule, something like this. So now if we use this updation rule, and let's calculate what is the value of x in the next iteration. So what is x1? x1 equals to, if you actually replace this I by 1, then you will get x1 equals to half of x0 plus n by x0, right? Now in this case, x0 is 5 and n by x0, which is 20 by 5, which is nothing but 4, right? So actually what is x1? It is the simple average of two numbers 5 and 4. Now interesting part is, see these two quantities, x and n by x. It is very interesting quantity. Now if we multiply these two numbers, we will eventually get the value n, which is 20, which is fixed for this particular problem, right? Now let's assume you have chosen a value for this first quantity x, which is, let's say, greater than root n, right? Like in this case, what is the value of x0? That is 5. Now what is our actual root? 4.472. So that means 5 is greater than that root n. So if this first quantity is greater than root n, then of course the second quantity must be less than root n, because if you multiply, you need to make it n. So it can only happen if another quantity is in opposite position, means it is less than root n, right? Then only this multiplication will give you the n. So therefore, interesting part is, if the first quantity resides in region R1, then the second quantity n by x always will reside in the other region R2, or vice versa. So let's mark the n by x0 over here, right? Now the next step is, we want to take the average of these 2 points. Now you know, if you take the average of these 2 points, So the average number will lie in between this 5 and 4. So let's say the average of these 5 and 4 will just assume that it actually stays here. Now if you look, this is what your x1 value, which is closer to the actual root rather than the x0, and that is what our objective. Every time when you update your x, that should be closer than the previous value, right? Closer to the actual value with respect to the previous value, right? So therefore this new point is more close to this actual root, right? So that means our mathematical philosophy are still intact. Now in approach 1 we have seen every time whenever we update using this formula xi equals to xi minus d or xi equals to xi plus d, we have used these two formula in our approach 1. There as well, every iteration we are actually improving. Only thing is that how the rate of improvement is different in both these two approach, but as far as the computation's correctness is concerned, both of them are correct. Both of this approach 1 and approach 2, they are creating the monotonically decreasing sequence of errors. Now one may be fast, another may be slow, that's a different issue, but both will eventually converge to that actual root because both of them are creating that converging sequence. So I hope it is clear to you. So therefore, so now in the iteration 2, that is x1, actually I have calculated 4.5. So I actually mark this point, and what this process is doing, it sends the value of x from 5 to 4.5. And if you calculate the error, the amount of error here is this much and amount of error here is very small. So the error is also getting reduced. If you remember, in approach 1 also it has happened, but it has not happened that much faster way. It was little slower because every time you are reducing by a constant amount d. Here you are jumping towards the actual root. So this method is much more faster. Okay. Now, so once I come to this x1 point, what I will do, I will again check whether this is the correct answer or right answer or not. So I will again re-execute the step 2, whether the new x is equal to n. If so, then stop, or otherwise again you update by using step 3. So that means you need to execute 2 and 3 repeatedly, right? So the next step, step 4, repeat step 2 and 3 until you reach to the actual answer. Now let's proceed. So we are in x1 here. So now x1 is this one. So what we need to find, we know that x1 equals to 4.5. So now we will find the quantity n by x1, which is 20 by 4.5, right? Now what we'll be doing, we will calculate x2. How should we calculate x2? Your x2 will be equals to half of x1 plus n by x1. So that means half of your 4.5 plus this value. So then this is what my n by x1, which is 4.44, and if we take the average of these two, that will become the x2, that is the value in the third iteration. So see, it is even more closer. So we are actually reaching to the accurate answer. Now within 3 iterations, if you notice properly, after 3 iterations the value of x converges to the actual root n. But in approach 1 we have seen we get that actual result after 12 iterations. So it is much faster with respect to the earlier approach. But see the important point here, both the approaches are correct. One approach, the second approach, is faster than the approach 1. So that is the only difference. Why? Because of the different update rule. It has a very it has lot more speed than the previous one. Okay. Now this method is famously known as Babylonian search method, which was invented long back 1800 BC. So it's a very elegant computational approach. Even long back people have invented it. So now let's proceed. So we have seen some steps, right? In approach 1 and approach 2, both cases we have seen certain steps. And what is the content of the steps? It's nothing, it's certain computations. X0 is 5, it is a computation. That means I'm assigning 5 to X0. I'm doing some more computation, and based on the result I'm deciding. So all these things actually is a kind of a computation. So this list of instruction, every instruction involves certain computations. So the above finite list of instruction in approach 1 and approach 2 both is known as algorithm. And this algorithm as a whole describes the entire computation strategy. Okay, so our question was, what is computation? And we found computation is nothing but step by step you need to do some calculation, and based on that you decide what is the next computation. So, and then if you formalize this, and if you can write it in that manner, step 1, step 2, step 3, step 4, then we say it's an algorithm. So now onwards we will not use the term computation anymore, we will say the algorithm. Okay, otherwise mostly they are synonymous. Okay, now one more very important thing we should remember: algorithm is something which has certain properties. See, when we written down all these steps, it's not that it arbitrarily we have written down. It has certain formalization. You need to maintain some standards, right? So let us see what are the features that an algorithm always should have in the next section. So what is the properties of algorithm? First, input. So every algorithm should have 0 or more input. Now for Babylonian search, what are the input? The value of n, which is 20, and maybe the value of x0, the initial approximation 5, because these are the values which you need to provide to the algorithm to start with, right? So therefore we say these are the inputs. Here in this algorithm we have 2 inputs. Of course there are algorithms which doesn't have any input. We will see it later when we run some program, that point. Okay, next point is output. And what is the important property of output? Every algorithm must have 1 or more output. So in the Babylonian search method, what is the output? The answer 4.472, the actual square root which we are trying to get. So please remember, algorithm may not have any input, but algorithm must have at least 1 output. If you don't have a single output, at least you should not say that that is an algorithm, even though that finite instruction list or and finite computations list, that will not be an algorithm unless you have an output, okay, of that. So therefore these are the very important thing. Now the third property is the definiteness. Now what is definiteness? It is actually saying that every step must be precise and unambiguous. Now what do you mean by precise and unambiguous? So if you remember, in our Babylonian search method we have said that or if you remember our approach 1, there we have said if x into x is greater than n, then xi decrease x by d, right? Because if it is greater than n, we need to decrease it. Now whenever this condition satisfies, then immediately we need to execute this decrement process, right? Now let's say this is step 1. Now in the same algorithm, in step 2, I am adding again another line: if x into x is greater than n, then increase x by d. So what will happen? For the same condition, x into x is greater than n, once I am saying decrease x by d, and the next step I am saying increase x by d. So these are ambiguous steps. They are opposite in nature. The same step, same condition, you need to do 2 different things. So which one is correct? So those kind of steps are known as ambiguous steps. So there should not be this kind of steps one after another, so that it will create ambiguity for the algorithm. So we will not have this kind of ambiguous step. Every step should be precise. When I am saying if x into x is this, then I will do this, that means no other thing I will do, only that thing. Very precisely you need to define, right? So this is what the example of one definiteness property. And one more thing is very important, is the finiteness. So every algorithm must terminate after finite number of steps. So if I take the same example, let's say approach 1, what we have done in approach 1, we have, this is what my actual route, and we started from any point. Now if it is greater than the actual route, we reduce it, and then we still reduce it. Now whenever we come to the other side, we start increasing. But please remember, at the time of increase, you have this increment that is much less than the decrement which you have used earlier, right? So therefore now we are using a increment which is less than the decrement used in the last phase. So similarly, when you again start decreasing, you need to use even lesser length. So instead of that, let's say what I am doing, same algorithm, what I am doing is that I have a point here, this is what my actual route. Now I am decrementing this, let's say here, then again I am decrementing, I come to the other side. Now when I want to increase it, let's say instead of using this formula di, what the formula I have used, di equals to 1 by 10 of di minus 1. This is the formula I have used. So that is the reason now your increment will be 10% of the previous decrement. But if you do something like di equals to 2 into di minus 1, that means 200%, which is more than 100%. So that means now you need to increase by twice the amount, previous amount. So then the point will come here, right? Because this distance should be twice of this distance. Now again, now I need to decrease the value. How much I will decrease it? I will decrease by the twice of the previous value. So previous value of this much, now I will decrease it by 2 times of that length. So I will come here, then you will increase by the length which is twice of this length, right? So it will go even further. So what is happening? You are never going to hit to that actual route, you are going far away. But actually in the approach 1, iteration by iteration we come close, right? We come closer to that actual route. But if you use this formula instead of the above one, you will go further away. Now you said when x into x will become equal to n, you stop the algorithm. But if you follow this principle, every iteration you are going far away from the root. So therefore you will never find this match in the algorithm. Even though you are running for infinite number of times, it will keep on moving away from the actual root, so the algorithm will never stop. So this is what known as infinite algorithm. So you should remember, you need to design your algorithm in such a way so that after finite number of steps it will terminate. So therefore these terms are very, very important. So the last but not the least is the effectiveness. What is effectiveness? Again, it's very simple. The algorithm steps must be basic and simple so that every layman can understand what you want to do. If you have a list of instructions stepwise and that instruction list has following properties, then only we will say that instruction list is an algorithm. So dear learners, so we have what we have seen. We can solve a problem in many different ways based on your logic behind the problem, logic behind the solution. Some methods should be faster than other methods, but please remember, every method must be correct. Until and unless your method is correct, you will not get the final answer. But if 2 methods are correct, that doesn't mean both the methods are same. because based on the logic, some method may be better than the previous method as far as the speed is concerned. So you need to remember all these points. Your algorithm must be correct, and then your algorithm must be efficient. We should use as less as possible iteration to get the final result. So these are the actual skill of designing algorithm. So one more important thing is that we said computationally solvable problem, and what we are seeing the term algorithm, right? Now what we are saying, if you have a computationally solvable problem, that means you have the algorithm for that particular problem, right? Or reversely, if there is an algorithm exists, that means there must be a computationally solvable problem associated with that algorithm. So it's very important to understand, right? Now finally, let us see what are the points that we have learned in this module. First, we have learned that algorithm is a finite list of instructions with some properties like your input, the output, the definiteness, the finiteness, and effectiveness. And we have also seen that any computationally solvable problem always has an associated algorithm. Now, dear learner, please remember this point. Whenever you have a new problem, you can design many different algorithms for that problem. But the most important point is we should design the algorithm in such a way that it should take the minimum number of steps to be executed, and that particular algorithm is the best algorithm for that problem. So finding out the best algorithm for any problem is a fun and very challenging task. So therefore, in our upcoming module, we will discuss algorithms for many different problems, and we will see some implementational challenges while executing the algorithmic steps in your digital machine. I hope you have enjoyed this session. Thank you. We'll meet again. Till then, have a great time.